Hi guys, thanks for tuning in. In this video, we're going to talk about Stokes Theorem, which is the capstone theorem of this course. The main idea here is we want to be able to compute the net flow of a vector field along a closed curve in three-dimensional space. Now, we already handled this for open curves. So 2 videos ago, we computed some path integrals for computing the net flow of a vector field along an open curve. But what we want to do in this video is generalize the Gauss-Green theorem to three-dimensional space so we can kind of handle the idea of computing the net flow of a vector field along a closed curve in three-dimensional space. In some ways, this will be similar to what you saw in lesson 12, where we lifted up the Gauss-Green theorem into the divergence theorem. But for the flow along situation, there's actually a lot more subtlety in this construction than you might think at first. So why don't we go back to two-dimensional space first, and then we'll build back up to three-dimensional space. So in the 2D case, we had two different computations that we could run. As long as we had a closed curve and no singularities encapsulated in our curve, we could either do the path integral, where we computed the integral of field dot tangent, or we were able to do the double integral over the interior. We did the double integral of the rotation of the vector field. And that was the Gauss-Green theorem that handled things in two-dimensional space. Now, in the two-dimensional case, we needed a counterclockwise parameterization of our curve. And that was pretty straightforward. Everybody knew how to look at a graph and say what clockwise or counterclockwise meant in that two-dimensional plot. But the idea of counterclockwise or clockwise doesn't really make as much sense in three-dimensional space. Now, you probably don't think about that on a regular basis, but clockwise and counterclockwise are problematic in 3D space. For example, here's a surface that lives in three-dimensional space. And how do you say whether these tangent vectors along this boundary curve go in the clockwise or counterclockwise direction? Now, you might immediately say, oh yeah, I actually think that that's going to be counterclockwise, but that's based on a bias towards the North Pole, right? You're imagining that you're standing on top of that surface, and relative to standing on top of that surface, those tangent vectors are counterclockwise relative to your position. But three-dimensional space isn't oriented in that same way. For example, if you were wearing a spacesuit and you were out in outer space, the idea of clockwise, counterclockwise, and top and bottom become a little bit more nebulous, a little bit more hard to pin down. So that's why I used Spider-Man in this picture, because Spider-Man also doesn't care about top or bottom, right? So when Spider-Man's standing on top of the surface, those normal vector or those tangent vectors are traveling counterclockwise relative to his position. But he could use his Spider-Man superpowers and go to the bottom of that surface. And in that situation, now those tangent vectors are clockwise relative to his current position. So we could usually figure this out by using what's called the right-hand rule. So the way we handle this is we just designate whatever side of the surface we want. We call it the top side of the surface. So basically plot a normal vector and say, so instead of Spider-Man, plot a normal vector. That's in place of Spider-Man, you could put a normal vector there and then say relative to that normal vector, those tangent vectors are counterclockwise. And the right-hand rule kind of helps us with this. So imagine your thumb going with your normal vector. And then as long as you use your right hand, we're going to say that the direction that your fingers curl in is going to be defined as counterclockwise. So relative to my normal vector, or relative to Spider-Man, those tangent vectors are oriented counterclockwise. And that's what the right-hand rule is. Sometimes students will overgeneralize the right-hand rule. The right-hand rule doesn't do any computations for you. The right-hand rule doesn't tell you the net flow of a vector field along a closed curve in three-dimensional space. All the right-hand rule is doing for us is helping us to define what we're going to call counterclockwise in three-dimensional space. So your thumb travels with whatever you're calling the top, whatever normal vector you're plotting to say that's the top of the surface, and then your fingers on your right hand are telling you what direction counterclockwise is. What the previous slide showed us is that it's really important to designate a top side for our surface so that we can say what counterclockwise and clockwise mean. One issue that we run into in three-dimensional space, though, is perhaps surprisingly, it is not possible to orient all surfaces. Basically, you would think that it's pretty simple to just take any surface and say, oh, here's the top side and here's the bottom side. But there are surfaces out there that cannot be oriented, non-orientable surfaces. And those types of surfaces are going to be resistant to Stokes Theorem because Stokes Theorem is going to depend upon having a surface that can be oriented with a designated top side and a designated bottom side. And probably the most famous example of a non-orientable surface is called the Mobius strip. Watch this little animation. I have a normal vector that's traversing along this Mobius strip, and as it goes on its journey, it starts on what you would think of as the top side, then flips to what you would think of as the bottom side, and now it's back to the top side. Well, I'm misusing the words top and bottom here because this normal vector is traversing the entire surface. It doesn't have a top side or a bottom side. This surface, surprisingly, only has one side. If you were a tiny little ant walking along this surface and you were taking a little trip here, you would end up managing to traverse the entire surface just from walking along. This is a non-orientable surface, and you can make yourself a Mobius strip. It's not very difficult. You take out a sheet of paper, cut off a strip, and then just put a half twist into the strip and then glue it together or tape it together. And that half twist gives you a Mobius strip. And of course, now you're ready for a famous joke. Why did the chicken cross the Mobius strip? So there's a chicken to get to the same side. Oh, come on, that's a classic math joke. A Mobius strip only has one side. And everybody knows that the best kind of joke is the joke where you have to explain the punchline to people. So you guys should use that one. All right, so we've run into a few challenges so far. So let me summarize all those challenges and how we've dealt with them, and then that will lead us into Stokes Theorem. So first of all, talking about flow along a closed curve in three-dimensional space, the words clockwise and counterclockwise lose a little bit of their meaning unless we're able to designate a top side to our surface. And then our boundary curve, we could say if that's parameterized in the clockwise or the counterclockwise direction. So clockwise, counterclockwise, less meaningful in 3D. Our fix is designating a top side. What happens if you can't designate a top side? What if you have a Mobius strip? Well, then you're going to be in trouble. Stokes Theorem is not going to work for us. We are going to require an orientable surface with two distinct sides in order for this theorem that we're about to introduce to work as expected. And then another problem that we dealt with over the course of these videos, we needed to generalize the notion of rotation of a vector field in 2D to some sort of three-dimensional version. And that's when we came up with the curl of a vector field, which was a three-component vector that captures all three planes of rotation in three-dimensional space. Right, now that we have all of these puzzle pieces fitting together, we can introduce Stokes Theorem. So here it is, the big capstone theorem of the course. Let's say we have a vector field m, n, p, and let's suppose that we have an orientable surface R with a boundary curve C, and we have that curve C parameterized in the counterclockwise direction. And let's also suppose that there are no singularities on the surface R. Then we have the following. We have the integral of field dot unit tangent equals the surface integral of curl dot top unit normal. Looks pretty darn similar to the Gauss-Green theorem, right? It's a correspondence between a path integral and this looks like a double integral, but we think of that as a surface integral. So a correspondence between a single integral and a double integral, very similar to the Gauss-Green theorem. We just have a lot more caveats. a lot more little tiny issues to deal with in order to make that theorem work as expected. And we do need some notation here. So the surface integral is the surface integral of curl dot top unit normal. And so we need to remember how the curl of a vector field is defined. You can memorize this formula, or you can memorize that 3×3 determinant formula. That's up to you. And remember that this entire equality breaks down if our surface is not orientable. So it is not possible for our surface R to be a Mobius strip. But most of the things we're going to deal with, if the surface is a disk and the boundary curve is a circle, yeah, no big deal. That's going to work fine. If our surface is a filled-in ellipse and our boundary curve is the ellipse that runs along the boundary, no big deal. That's going to work as expected. So as long as we don't have something like a Mobius strip, Stokes theorem should work pretty darn well for us. Now, some of you guys are going to go on to advanced physics courses or perhaps other math courses where Stokes theorem is going to come up again, and I want to show you the notation that you might see in a physics book or a traditional Calc 3 textbook. It should be somewhat familiar at this point since we've done quite a bit with del so far, but you're not going to see the notation curl field written out. You're going to see del cross F. You're probably also not going to see any sort of top unit normal or top normal written out. You're just going to see n. So keep that in mind. There's slightly more compact, slightly more traditional notation that you might see in Wikipedia or a traditional textbook, and I want to make sure that you recognize these variations that don't look exactly like what you see in the net math course but mean the same thing. So again, curl field and del cross F mean the exact same thing. One other thing I should point out is Stokes theorem in 3D that actually reduces to the Gauss-Green theorem when we're talking about the xy plane, when we're talking about two-dimensional space. So if you think back on stuff you previously knew, you might have a vector field m comma n in two-dimensional space. We can embed that in three-dimensional space. We could write f as m comma n comma 0, and that would be an embedding of m comma n within three-dimensional space. Basically just contain it all to the xy plane, all your rotation to the xy plane. And if you can compute the curl of m comma n comma 0, well, when you crunch the numbers on that, you just get 0 comma 0 comma the rotation of the vector field. Oh, so there is this formula from lesson 8. It was living in 3D all along. It was just living in the z component of a vector that had 0 comma 0 at the beginning. So it makes sense just to write this scalar portion and not write out that entire three-dimensional vector. So long story short, Stokes theorem and Gauss-Green theorem can be tied together if we take our top unit normal to be 0, 0, 1, plug that in right here, take 0, 0, comma rotation of our vector field, take the curl that we computed, plug it in there. When you take this dot product becomes a scalar quantity. It's just the rotation of the vector field. And so we get back this more familiar formula that we remember from lesson 8. Now that we've established Stokes theorem, let's use Stokes theorem for a concrete example. So for this example, I have a vector field y plus z, comma x plus z, comma y plus x. And we're going to let R be an orientable surface, right here. And we're going to let C be the boundary curve of that surface. And we want to compute the net flow of our vector field along our boundary curve C. And Stokes theorem is going to be very helpful for this. Let's see why. So let's try to crunch the numbers for the curl of this vector field. So for example, let's look at just the x component. We have dp dy minus dn dz. All right, so dp dy, so the partial derivative of p with respect to y is 1. And then dn dz, the partial derivative of x plus z with respect to z is again 1. Oh, 1 minus 1 is 0. And actually, for all three components, when you crunch those numbers, you get 0, comma 0, comma 0. the curl of this vector field is 0, 0, 0. Now let's try invoking Stokes Theorem. Let's see if this can help us. So we know that Stokes Theorem is a correspondence between a path integral along the boundary and a surface integral over the interior surface R here, or a surface R that has C as its boundary. All right, but wait a minute. The curl of our vector field is 0, 0, 0, so let's plug that in. Oh, and I haven't even really done any calculations yet. I haven't done anything. Actually, I don't even know a parameterization for my surface R or a parameterization for my curve C, but it doesn't seem to really matter because 0, 0, 0 dotted with any top unit normal that I could possibly compute, this dot product is going to come out to 0. And I know that my surface integral of 0 is going to equal 0. Oh, so I can already draw a conclusion. The net flow of this given vector field along this given curve is equal to 0. And in practice, this is probably the most useful application of Stokes' theorem when we're crunching numbers. If we're lucky enough to have a scenario where the curl of our vector field is equal to 0, 0, 0, then it's beneficial to change over from a path integral to a surface integral over some surface R, and then the fact that curl turns into 0, 0, 0 makes this into a very easy calculation. Finally, guys, I'd like to close out this video by talking about Stokes' theorem in practice. In reality, how do we typically apply Stokes' theorem? Now, the previous example was awesome. We had a path integral that was going to be probably a pain to compute. Some curve C that probably had a fairly ugly parameterization, and computing that path integral would probably be somewhat unpleasant. However, we computed the curl of our vector field and we knew it was equal to 0, 0, 0. So we invoked Stokes' theorem. We said, I don't want to deal with this path integral that was going to be somewhat unpleasant. Instead, I'm going to switch over to a surface integral. I'm going to plug in 0, 0, 0 for the curl, because that's what I computed. And 0, 0, 0 dotted with any top unit normal that I could have ended up computing for whatever my parameterization for R was. That dot product was going to equal 0. So my surface integral ends up equaling 0, and I'm done. So that was a nifty little shortcut. However, you need to start asking yourself, wait, what would I do if I was in a situation where the curl of the vector field was not equal to 0, 0, 0? In that case, it turns out that Stokes' theorem is basically a set of choices. You get to either choose a path integral along your boundary curve C, or you could compute the surface integral over the surface R, a surface R that has C as its boundary curve. And when you're faced with option 1 or option 2, most of the time option 1 is going to be more desirable. Think about it. You guys have been computing path integrals for several chapters now, and you're very good at them. Putting a path integral into 3D space doesn't make it that much more difficult. However, surface integrals, those can be kind of a pain because basically your picture looks like this. You've got some curve C living in three-dimensional space, and you've got some surface R that has living in 3D space. So something like this. Just drawing in some axes here so the picture looks a little bit better. Okay, so you have a curve C living in three-dimensional space and a surface R that has C as a boundary curve. Either you could just use path integral formula to compute a path integral along the boundary. You guys are already pretty good at that. Or you could do the work of parameterizing R, and then after you parameterize R, compute the curl of the vector field. Then plug your parameterization x of st, y of st, z of st into the curl formula. Then compute some normal vectors for your surface. Then take the dot product between those normal vectors and curl of x of st, y of st, z of st. And then after you're done with that dot product, then you have to compute your surface integral. Well, when I'm faced with those two options, I'm probably going with option number 1. I'd rather just compute a path integral along that boundary curve C. So, long story short, in practice, Stokes' theorem is great for shortcuts and it's great for conceptual understanding, but it's not necessarily a great computational tool, and you'll see that reinforced in the courseware for lesson 13. All right, guys, so that kind of closes out this video. In my next video, which is going to be the last video of this course, we're going to talk about gradient fields.